Hello and welcome back. Um, so I'm going to be talking about Advent of Code Day 2 today in 2022, trying to catch up, trying to catch up on some of these videos. So in this problem, we are going to be playing a series of rock, paper, scissors games, and in our input, the 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 move that our opponent is going to be playing is denoted by A, B, and C, which stand for rock, paper, scissors, respectively. And then we have YXC, which also stands for rock, paper, scissors. Um, so we're going to be playing a series of games, and then we have to score those games. So we get points based on the move that we play. So 1 for rock, 2 for paper, 3 for scissors. And then we also get a score based on the outcome of the round. And it's 0 points for a loss, 3 points for a draw, and 6 points for a win. Um, and there's just some explanation here. And the idea is that we resolve all these rounds, and then we perform this scoring. And the question is, what is the total score after playing all of those rock, paper, scissors games? Fair enough. So before we even talk about parsing our input, I thought it would be good to talk about our strategy a little bit. One of the first things that I'm going to do is I'm going to set my index origin to 0. The default is 1. So all that means is like if I do iota 10, it prints out the numbers from 1 to 10. Index origin 1, which is the default in Dyalog, means that the first element of a list has index 1 rather than index 0. Now, if I set IO to 0 and I do IO to 10, now it starts counting from 0. And when we're doing modular stuff that wraps around back to 0, this is just going to make things a little bit nicer. Okay, so I think that it would be good if we mapped our input onto some indices. So if we have rock, we have paper, and we have scissors. It would be nice if we could map them onto the range 0, 1, 2. So if I do like that. And the nice thing about this is that say we have a series of moves like we have rock, we have paper, we have scissors, rock, paper again, then scissors. In order to perform the scoring for the moves, all that we have to do is add 1 because we're getting 1 point for throwing rock, 2 points for paper, and 3 for scissors. And then if we add them all up, we can get the total score for our different moves. So I think that would be it's useful to map our moves onto this range. And if we look at the game results, we have the following scoring. We have 0 points for a loss, 3 points for a draw, and 6 points for a win. And the interesting thing is that if you just divide these by 3, you get the same range of 0, 1, and 2. So if we can map our losses, draws, and wins into this range, then if we multiply those values by 3, then that gives us our total score for the results of our different matches. So if I do, just to make this explicit, so we have lose, draw, and win. These will also be in the same range. And the other nice thing about being in this range is it makes it easier to work with modular arithmetic, which is going to play a big part of this. And I'll explain how we're going to be using that here in a bit. But yeah, so essentially our strategy is to map all of the rock, paper, scissors values in our input onto 0, 1, and 2. And then when we figure out the results of those games, we also want our losses, our draws, and our wins to map onto this range. Okay, so as usual, we will get our input. And so we have, all of these lines with, the the different values for the elves, it's going to be A, B, and C. For us, it's going to be X, Y, and Z. Now, there's not really any use in having like different domains for their moves versus our moves, so we want to map these into the same domain. If I mix this input, I get a matrix, and actually these are 3-element matrix. Each row has 3 elements because there's a space in the middle, and we don't really want the space, so we want to select the left and right columns. There's a few ways to do this, but I think the cleanest is just to do a selection vector. So we select the left column, drop the middle column, and select the right column. And that gives us this. Now, we can index into this using quad A, which gives us a string containing all of the uppercase letters. And if we do quad A index of, that gives us these numeric values. But like I said, we don't want to have different domains for their moves and our moves. It makes it a lot easier if they're in the same domain. So if we look at the right column and we just look at the unique values, we can see that they consist of the numbers 23, 24, and 25. And we want to map those onto 0, 1, and 2. And so we can just do 23 mod here. It's not going to affect the left column because it doesn't have any values greater than 2, but it will cause the right column to wrap around back to 0, 1, and 2. So great. And now we have all of the elves moves and we have all of our moves mapped into the same domain, which this table I'm going to assign to, I don't know, B, because we're going to be looking at it a lot. So now rock, paper, and scissors are all mapped into the same domain. It's going to be a little bit easier if we can work with these two vectors independently, their moves and our moves. So if I transpose this, I get 2 rows here, and then I can break it down so I get 2 separate nested vectors. And I don't know where these backslashes are coming from. And I can assign these to them, which is the first vector, and us, which is the second vector. So these are all the moves that the elves are going to throw, and these are all the moves that we are going to throw. Okay. Now, how do we actually evaluate whether we win a game or not? So let's see. If we look at, let's take the second row of B, and then if I just like 9 row this to extend it. So like let's say that we throw rock, right? What are the possible values that the elves can throw? Well, they can throw rock, paper, or scissors. They have 3 choices. If they throw rock, then that's easy. We know that it's a draw. If they throw scissors, then we win. So rock wins against the element behind it, right? If they throw paper, then we lose. So rock loses to the element in front of it. Same for paper. If we throw paper and they throw rock, then we win against that, but we lose to the element in front of it, scissors. And if we look at scissors, scissors wins against paper, but loses against rock. So basically for each, if we order the list of moves like this, rock, paper, and scissors, then each element draws against the same element, makes sense, loses against the element behind it, and wins against the element in front of it. Now it's a little bit tricky with scissors and rock because rock doesn't have any element behind it, but we can use modular arithmetic to cause these values to wrap around. So if we look at iota 3, which is just the elements 0, 1, and 2, and we look at the difference for each element. And maybe it's better if I do like 1, B, this, 1, B. Okay, yeah, so now we have a nice table. So you can think of, you know, here on the leftmost column, we have the values that we're going to throw. And in the upper column, we have the values that the elves are going to throw. So, for example, if we throw rock, then it's going to be, a draw here. And then we have these negative values, which is kind of weird. So the way modular arithmetic works with negative values, so if we take 0 mod 3, that's 0. That makes sense. But if we have a negative value here, then it starts wrapping around from 3 again. So negative 1 mod 3 is 2. Negative 2 mod 3 is 1, right? So in order to map these values into our 0, 1, 2 range that we want, if we look at the table again, that's what we're working with, we can do mod 3 here to bring the negative values into this range. So you can see from our table that we want losses to have index 0, draws to have index 1, and wins to have index 2 because it makes the scoring much easier. But if we look at this table, like, that's not happening, at least with the draws. So we can see that we want the draws to be 1, and they're currently 0. So we can just try adding 1 here before we do the mod 3, so that the values still fall within this range. Okay. And now, so if we throw rock and they throw rock, we get an index of 1, which if we look at our table again is a draw. That's what we want. If we throw rock and they throw paper, then that should be a loss for us, and that's index 0 here, and that is indeed a loss. If we throw rock and they throw scissors, then we should win that, and we see in our table that index 2 indicates a win. So this looks correct. You can, look at the same values for paper and scissors. The way to think about this is basically we're looking at the difference between our moves and their moves mod 3, and we're just adding 1 because, so like here we determined that every element wins against the element directly preceding it and loses against the element directly in front of it. So if we do mod 3, this negative 1 then becomes a 2, and this the 1 here for the loss then also stays a 1, right? And if we add 1, then we're shifting everything to the right, and 2 will become 3, and that wraps around back to 0. I hope this makes sense. But basically, we're just taking the difference, and we're getting these negative 1, 0, positive 1 values, and we're adding 1 to shift them to be within the range of our table here, where 0 is a loss, 1's a draw, and 2 is a win. And the really nice thing about this is that if we then multiply these results by 3, we get our proper scoring. So rock versus rock is a draw, and now we get 3 points for that, which is what we want. A loss against paper gives us 0 points, which makes sense. And then a win against scissors gives us 6 points, which is what we want. Okay, so basically we look at the difference between our moves and their moves. We add 1 to shift the range over, And then we do mod 3 to bring everything into the proper 0, 1, 2 range. And then we can multiply by 3 to get the proper scoring. So if we do if we do us minus them, then that gives us this vector, and we add 1 to shift things over, just like we were talking about. And if we do 3 mod, that brings everything into the 0, 1, 2 range. If we multiply by 3, that gives us the scores for the different match values. And then all that we have to do to calculate the final score for each game is incorporate the fact that we get points for our move as well. So we get 1 point for rock, 2 points for paper, 3 points for scissors. And that's just going to be our moves, so U plus. And then we have to add 1 because our moves are 0 indexed. So right now 0 is rock, 1 is, we can look at our table again. 0 is rock, 1 is paper, 2 is scissors. We have to add 1 to these values to get the score of 1 for rock, 2 for paper, 3 for scissors. So we're just adding 1 here. That gives us this vector, and then we just have to sum it to get the final scores for all of the different games. So we get 13,005, and for part 1, that is indeed the answer. So we can really simplify things by using modular arithmetic to stay in this range of 0, 1, 2. And the nice thing about being in that range is that it makes the score calculations very easy as well. Yeah, so that's part 1. And then for part 2, it's a little different. So now X, Y, and Z denote the different game results that we need to attain. So X means we need to lose, Y means we need to end the round in a draw, and Z means you need to win. The nice thing is that we're already operating in this range if we look at our table. So our rock, paper, scissors values are the same as our lose, draw, and win values. They're all mapped into this domain of 0, 1, and 2. So we don't need to do any modification of the input to be able to determine the value that we want the game to end in. And then, so given the match result, we need to figure out what to throw or what move to make in order to attain that match result. And we calculate the total score for each round in the same way. So we get points for our move, and we get points based on the match result. Okay. So if we look at this again, let's say that they throw paper and we want a draw. So paper is 1, and if we want to draw, we just keep the same value. So we would also want to throw a 1. You can think of this as adding 0 to the index of paper, right? If they throw paper and we want a loss, then we can subtract 1 to go back to rock. We would want to throw rock in the case where we want a loss against paper. So paper minus 1 is 0, and 0 is rock, right? If they want if we determine that we want a win, then we would throw scissors, which is paper plus 1 turns into 2, right? So let's see. So now we end up in this situation where, let's see what I can do here. If we do iota 3 plus 1 jot dot plus, oh. So we get this, then if we do 3 mod, we get this, and then we can do, it's going to be lose, draw, win in the left side. And then on the top, we'll have it's 1, index B, counting first, like so. Okay, and we'll have our table here. So if you can read this chart as now our values indicate whether we want a loss, a draw, or a win. And they're going to throw, some move, and we have to determine what to throw in response. And these 0, 1, 2 values are just indexes into our table that denote rock, paper, or scissors. So if they throw a rock and we want to lose, then we would throw 2, which is scissors, right? If they throw paper and we want to lose, then we would throw a rock, right? If they throw scissors and we want to lose, then we would throw paper. And for draws, we just throw the same elements, but for wins, we throw these elements, right? So what's going on here? Well, we determined the values that we need to we determined the values that we determined the values that we need to add to the different moves in order to get the different match results that we want. So like if they throw paper and we want a loss, then we have to do -1 to get rock. If they throw paper and we want to draw, then we do +0 to get the same result. And if they throw paper and we want a win, then we add 1. So our moves are going to be in this -1, 0, 1 range. And we're going to be adding the moves together, but we can subtract 1 from our results of lose, draw, win, right? Because actually we don't want draw to be 1, we want it to be 0. We don't want lose to be 0, we want it to be 2. And we don't want wins to be 2, we want them to be 1. So we're just subtracting 1 from our values in order to get the match results. Hopefully that makes sense, but I think this table is pretty descriptive. So in this case, we take us -1 to shift it over like we need, and then we take them plus us in order to translate our shift into the move that they throw through. And then we're going to do 3 mod here to bring it into this 0, 1, 2 space. And then these are not match values. These are the moves that we want to throw in a particular game. And so we can do 1+ in order to bring it into the proper scoring range, where we get 1 point for rock, 2 points for paper, and 3 points for scissors. Now we need to add the scoring for the match results, but in this case, our match results are just the us vector multiplied by 3. So the us vector is 0, 1, or 2. We're basically selecting whether we want a loss, a draw, or a win. And just like we did with problem 1, we can multiply these values by 3 to get the proper score. So we do this, and then if we sum it, we get 11,373, which is indeed the correct answer. So it's a little bit confusing maybe, but basically we're just operating in mod 3 space, and we have our moves, rock, paper, and scissors mapped to 0, 1, and 2. We have our match results mapped into the same domain, so losses, draws, and wins. And then we're doing some shifting around of these values to get the proper computations, doing mod 3, and then because our the two things that we're getting scored on are the moves that we're throwing and the match results. And because they're in this domain of 0, 1, and 2, it's very easy to compute the proper score for each one. So for moves, we just add 1. And then for the match results, we multiply by 3 to get 0, 3, and 6. So if I put all this together, this will be part 2. We had part 1 up here. And then we did some parsing of our inputs here. And this is the entire solution for day 2. We run these, we should get the same answers. We can do a performance check, I suppose. So if we look at the function f, this will operate on W. As usual with performance comparisons, we're not counting disk access. P2, and then we can just output P1, P2. We'll assign P to our input. Yep, and then if we run F on P, we get these values. We can pull compx from defense, and we'll see how long it takes to run on the problem input. It's, I don't even, 75 microseconds apparently. So yeah, everything is pretty fast because we're just doing a bunch of vector math here. So way less than a millisecond. So yeah, not bad performance. This isn't, this problem isn't too crazy in terms of performance. I'm sure the difficulty will ramp up in later days. But yeah, that is day 2. Hopefully this was instructive. As always, thank you for watching.